1, 2, testing, testing. Okay, now I'm hot. Welcome back from break, and thank you for joining us again. This is Detect and Avoid, State of Play. The last panel was a little less technical. I think this panel is going to be a little more technical. I'm very pleased to be joined by some of the technical experts in this field. I'm going to start with my colleague Dallas Brooks, who Dallas is the director of the Ashore Center of Excellence and at Mississippi State. Oh, that's right. And then we have, boy, I need longer between sessions. We have Jonathan Daniels at Praxis. We have Allie Ferguson with Precision Hawk, and Paul Albuquerque with the FAA, and then Edward Lester, Ted. With Aeros, yeah. Ted. Yep. So we've talked a lot about beyond visual line of sight flight, and there are been a number of allusions to technologies, references to technologies that in fact support that. And there are many things that go into beyond visual line of sight. But one of the key is meeting the ability in Part 91 in 3 specific sections that basically see and avoid, and to be able to give right of way. And so there is no one performance standard for see and avoid in manned aviation. And what we see is there are many different ways to operate drones, just like there are many different ways to operate manned aviation. We do have one standard defined that came as a minimum operating performance standard, came out of the work of RTCA Special Committee 228. And that does define a detect and avoid standard for aircraft that, for the most part, are going up to and transitioning through Class A airspace. But it's a radar standard, and radars are heavy. They require a lot of energy and are not practical for many of the applications that we look at in the industry. So it really leaves us with the question of what is the state, where are we in all of this? And we're going to start first with Paul. And Paul, if you could lay out what is the real regulatory basis behind detect and avoid? What's the root that we're trying to meet? What's the root cause, the root requirement?
So I would say the function of detect and avoid is based on really under 107, there's 2 rules. So I wrote them down so I won't mess them up. 107.31 and 107.37. So one is the ability of a remote pilot to keep track of their aircraft visually. So the DAA would have to be a technology that is an alternate means of accomplishing that same task. And then being able to scan the airspace. So again, a technology that can scan the airspace in equivalent fashion and provide that information to the remote pilot. And then 37 is to yield right of way to all other aircraft under Part 107. So that's a tough challenge, and that's really what DAA for 107 means. For Part 91, it's 91.113, and the phrase is see and avoid. So really building a system that can appropriately do the same thing that a pilot would do by looking out the window, picking up other traffic, and taking action.
So you've done a number of waivers, safety cases around beyond visual line of sight. You're one of our experts in this whole area, which we're grateful to have you for that. What are some of the challenges you've seen with respect to DAA in supporting a safety case for beyond visual line of sight?
So I think one of the biggest challenges is really understanding what else is in the airspace. So airspace characterization, it's a really tough nut to crack. There's no defined way of really doing that. I know, Ted's been part of that for SC228, but really now that we're exploring a lot of different types of airspaces, a lot of different parts of the country, there's a lot of variables, and And that's one of the next big challenges, because that's really key to figuring out what the right performance requirements are for DAA systems. Because we know that there's no one set of performance requirements. There's a whole host of different types of operations, different types of air risks. It's not the same from one place to another. And so to really define a process for how to make that characterization. The other part, of course, is then linking an airspace characterization to a set of performance requirements. That's obviously an ongoing area that we're working on through, RTCA is a little bit more mature, but in ASTM F38 for some of the smaller drone applications, working on that problem.
So do you see these challenges mostly in the technical side, the policy side, including guidance, or both?
I think it's very much both. I think there are some technology solutions that are being worked on, but they're still maturing. Even RTCA, it's been a long time in the work, but we don't have, at this point, defined procedures in how to integrate that into certified aircraft, and then we don't have a defined pathway for going out and operating. It's something, General Atomics and NASA have worked on, but there's obviously more work to be done to make it more mainstream. And then in the smaller drone space, there's a lot of work in the developing standards for the technologies. There's a lot of work that will have to occur in how do we build a regulatory framework to use those standards. So I think it's definitely both.
Okay, so that tees up where we are from the regulatory, what requirements are we trying to satisfy, which brings us to you, Dallas. Where are we on the research that would support the kind of data that Paul, or an applicant would need to bring to Paul and company when they're applying for a waiver, exemption, or applying to operate under, say, Part 135?
Well, it's a broad question. What is the state of research in detect and avoid? And so I'm going to take a minute or two, and I'd like to walk you guys through sort of how this problem has been structured, what agencies, what organizations, and what companies have done solid work, and how that all sort of fits together into an approach to a convergence to the answer that I think that most of you are looking for. When we began this, I started in the UAS world about late 2004. I was in Department of Defense working for the Air Force at the time, doing airspace integration, and eventually ended up at OSD doing that as well, sort of where I sort of collated all 4 service programs into sort of one umbrella program that defined what we meant in terms of detect and avoid. Because at the time, the Air Force had a system, the Army had a system, the Navy had a system, the Marine Corps had a system, and all of them had different assumptions and fundamentals. And so as my job on the OSD side was to bring those efforts together and make sure we were all operating off of the same hymnal that said, this is what we mean when we talk about detect and avoid. And we staged some fairly simplistic but very important questions to sort of walk us through that process. The first was, how do we define what detect and avoid is? What encompasses that function? At what point when you've done these things have you done the job of detect and avoid? Right? That's number one. Number two is we needed to define what well clear is, because it's impossible to design a system to do something until you define what that something is. In this case, that something was, how much do I need to miss another aircraft by? What is that distance? What is that time? What is that altitude? How much do I have to miss by? Once I know that, technologically, I can work backwards to determine the performance of my system relative to the performance of my aircraft, relative to the performance of the other aircraft, to make sure that that indeed can happen. So that was question number 2, define well clear. Now question number 3 was, how do we define the acceptable performance of the system? So now we understand what it is, we understand what it needs to do. The third question is, how well does it need to do it? And then finally, it was determining the right combination of technologies and algorithms and human-in-the-loop participation to be able to meet all of that, to be able to meet those performance standards that have been set. So those 4 fundamental questions have driven detect and avoid research ever since I've been involved, so mid-2000s and even before. I'll take these really quickly to sort of give you an idea of what each one ended up in terms of progress has ended up in doing and who's doing it and how well it's being done today. The first is defining detect and avoid. Now, when I was at OSD, I stood up an organization called the Science and Research Panel, the SARP, that at the time was just the 4 services plus the FFRDC, such as MITRE, MIT Lincoln, and others. and also academia. So that was everybody we could bring in that was not industry. Not that we didn't love industry, but since we were working on government level standards, we had to do that within a government level construct. And so over a period of about a year, we had a lot of what I call skull cracking sessions, where you lock everybody in a room and you make sure that they don't leave until the answer gets codified. And so for defining detect and avoid, we did that. And that work had started actually at the FAA back in 2007, 2008. My good friend Steve George had convened 2-year-long workshops on doing just this. And they came out with some excellent work. And he involved folks from across the spectrum of the industry and from government. It was my job then, since for DoD, we were actually developing systems. We were building DAA systems. So we had to be able to justify through our acquisition and technology chains what we were building to, what specifications. So we took Steve's work and we basically granularized it. We added a little bit more detail, a couple more steps that were actually broken out. And then that became our roadmap. And I can tell you that all the DoD work that's been done since has followed those basic principles. So that work basically done between the FAA in 2007, 2008, and the SARP in 2010, 2011. So moving forward, the next question. How do we define well clear? That question fell almost exclusively upon the SARP. By now, the SARP had grown. So beyond just the DoD agencies, it was the DoD, FAA, NASA, and the Department of Homeland Security. So now we're working this as an interagency problem, right? And then later we were going to add even more agencies. But working through two halves of the problem independently. The first was how we define it for large aircraft operating at altitude. Jay mentioned that earlier. And that work ended up in the RTCA SC-228 minimum operational performance standards, right? And that I can talk to anybody about what those standards are at any given time, and so can Ted. And then the second piece was moving down as the industry has shifted towards a focus on smalls, away from DoD needs and more towards commercial needs. We tackled the question of what is well clear between a small UAS and a manned aircraft at low operating altitudes. And that work has since been completed. And it's also been published, this time in a draft FAA advisory circular, which is currently, I believe, named AC90-WLCLR, if I recall correctly. And that essentially was the SARP recommendations codified, and that's out for comment. Then the third question, defining the acceptable performance of the system. How good is good enough? So that's the work that's going on today. So there are a lot of different agencies that are working this. First off, the UAS Center of Excellence, which is an FAA body that is basically an umbrella organization of 23 of the top universities in unmanned systems in the country. I'm fortunate enough to be one of those member universities. And between the work that we're doing within Assure at the University of North Dakota, New Mexico State University, at Mississippi State University, at the University of Alaska Fairbanks, we are all evaluating, literally live fly evaluating various DAA systems and system components. So in some cases, we're evaluating sensors. We just want to find out how good the sensor is, how far out it can detect a likely manned aircraft, to what range, at what closing speeds, at what altitudes and changes, right? That work is going on now. Also, same time this is going on, through the FAA's Integration Pilot Program, more work is being done, and that is much more industry focused, right? That's in collaboration with multiple industry partners led by my friend Kathy Cahill at University of Alaska Fairbanks. So I think she's got some 40 or more industry partners that are participating in that IPP, and they're all bringing not just equipment to the table, but ideas and algorithms and systems and interconnectivity. So that work is going on now, and that work is some serious heavy lifting. But the folks who are participating in that, particularly from the industry side, are doing a phenomenal job of leading forward and sharing the data on their system's performance and making those systems available to test. And then finally, the next step is going to be in determining that right combination of technologies, right? Whether that be from the sensor side, on the integration side, the processing, the algorithms, that right combination that gets us to that magical place of being able to ensure that within the airspace we're operating, we're likely going to be able to maintain well clear to a very high degree. That work is starting just now in the infancy of its development, because first we need to understand the landscape of the technology, of the sensors, of the algorithms, of the processing systems. So that work is just now starting. But once we get to that point, we only have to get through those first 3 steps, which was defining detect and avoid, well clear, and acceptable performance, in order to turn industry and government loose on being able to apply solutions. That 4th step is not a prescribed solution, it's just understanding how well these components can work together and what the art of the possible is. So literally we are this close to being able to have some absolutely solid data on that performance piece, that 3rd piece, that turns everyone loose and says, okay, we understand what we have to do, to maintain well clear. We understand what that expectation is. We also understand what levels of performance are likely to be acceptable, though our approaches, which come from industry, can vary as long as they meet that performance standard. So, very long-winded answer, but I thought that this audience deserved to understand what we were looking to solve and how we got here and where we're likely to go next.
So I'm going to give you an opportunity for a longer answer. Take a deep breath.
Got it.
You ready?
Mm-hmm.
That's a lot to go through.
Mm-hmm.
I know I've got some operators up here who don't necessarily have all the solutions they need. I know I've seen a lot of safety cases, and as the complaints department heard a lot of folks say, we're not quite there yet. What gaps exist in the research? You did mention the performance, that you're not done with that, but I get a sense that there must be a larger gap somewhere. Otherwise, I would see happier faces on my operators.
Well, not all gaps are research gaps, right? So one of the things that I find interesting, so I've been in aviation for 35 years. I get safety and I get culture and I understand why the system we have works so well. So there will be times when I will point out things that I wish the FAA were doing, and there's also times where I will defend the FAA because I know that the reasons that they're doing those things are sound. And this is going to be one of those combination times. So in terms of the gap that I'm talking about, our entire aviation system is based on some very, very sound safety principles, but it's also based upon this burning desire within the FAA to make sure that the steps that they take don't squash, stifle an industry, that don't stop development and innovation from happening. Believe me, folks, it's amazing how careful they are about this. So just as much as they want to be safe, they want to make sure that they don't put you guys in a box that you'll never get out of. So that's important, because when they ask us to go through some very detailed and very rigorous safety evaluation processes, whether you're doing SMS and SOAR or whatever else, these are very prescriptive in process, but open in terms of how you implement them. And that works really, really well with very large established aerospace companies. If I'm Boeing, if I'm Airbus, I don't want the FAA to tell me what the answer is. I'm pretty darn good at developing innovative solutions. What I want you to tell me is what you're shooting for, and I will bring you not only the answer that I believe it to be, but I will bring you reams of safety information, reams of process information, and reams of data that back up my assertions. And now you can review that and say, you know what, Boeing, you know what, Airbus, you guys got it. Tweak these couple of things here and we can go with this. And this is traditionally where the FAA's safety review role is. It's not in making up standards and handing them down from on high. It's on having those standards actually come to them as proposals from very sound and very rigorous processes done by generally very mature companies. So now let's flip that script for a second. We're in the unmanned systems industry. We are all of the things that big aerospace is not. We're young, we're innovative, we want development cycles that last 18 months instead of 18 years. All of those things are things that 95% of the people that are in this industry, not people, of the companies that are in this industry are crying out for. We've got the tech, just let us use it. We've got the tech, just let us use it. And if you go through that list of companies that are in the unmanned space today, how many of them have certification engineers and big processes built to do aviation kind of processes? Almost none. So that's the gap that we have now. It's not that the FAA doesn't know how to do this, and it's not that the people who are doing the work don't understand what they want to do. It's a process intersection, right? So what most of you would like is for the FAA to say, here's your performance standard, here's how you meet it, go do that, and we're going to say yes. That's what you want. To get there, however, if the FAA were to come down with that process and for some reason they got it wrong, which all credit to you guys, but they're likely to do, because the first time you make a guess like this, you're likely not to get it right the first time, you can ruin companies. You can ruin an industry. The folks that spent all their IRAD dollars going this direction, all of a sudden it turns out they were wrong, and their investors pull out, it goes away. So what the FAA has done is extend you an invitation that says, here's a playbook. We understand it's a very tough playbook. It's sometimes an unwieldy playbook, but it's there. We're willing to work with you, however, that we're not going to hold you to an A320 standard for your small UAS, but we do want you to understand how to get there. And so what I think the way we close that gap, and I've seen it happen over about the last 2 years, is some of these smaller folks are educating themselves more about how that safety process works. I know that Jonathan Alley are two fantastic representations of that. Both don't come from giant companies, but both have really, really fine-tuned the needle on these processes, and they're working within them, but they're also stressing them from the side and saying that there are some times when what you're asking for doesn't make sense. So that intersection between old established processes that are extraordinarily safe and what we want to do as a young, innovative, and not quite mature industry in some cases, bringing those two things together and compromising to get to a middle position that meets an acceptable level of risk, a certain level of safety, and absolute integrated access for all users of the NAS. That's what we're trying to go to. And I think you'd be surprised at how close we might be.
So, Jonathan, you're one of those companies, and I've had the personal benefit of having some conversations with you that maybe there are still some gaps. I know you've been working on this challenge for some time. How are you meeting the challenge of DAA, and what are the challenges that you're seeing from the Praxis perspective?
So I always love following Dallas because he tees everything up fantastically. And I have
come on, give some props to Paul, too.
Definitely, and Paul as well, thank you. The part of the challenge we've run into is it's not a crawl, walk, run process. It's a baby flop, and then we'll get to the crawl and walk. So one of the things that when we jump on the BB loss and people start looking at, how do we get there, and detect and avoid becomes such an issue, that we have to realize there is that baby flop phase. And I say that because there's a lot of people, not necessarily in the audience, but out in the industry, that's not BB loss haters, right? If you have visual observers or that sort of thing, that you're not true BB loss. And that they kind of try to marginalize what we're doing. And the challenge with that is that we have to understand that in test environment, that's redundancy. So we could have the perfect system, ground-based, air-based, hybridized, but in order to do a true test, you have to test that redundancy, and currently that redundancy is the visual observers. All right, so I started up by saying that because when it gets down to what's good enough, we end up using the visual observers as part of the test method. So when we got our first BB loss waiver just over a year ago, a whole part of that was how do we use the visual observers as part of the test method to test the equipment and performance that we're looking in there. So every time there's a visual observer who identifies an aircraft or some type of ground traffic, that's documented and then compared with what the technology we're using to meet that requirement is. And that allows us to bounce back and forth. And sometimes we just have visual observers out there who are just tracking that data as well, which I have to thank Ali for because that was part of the discussions came out of the Pathfinder project and those recommendations out there. So I say that is what are the challenges. It never goes fast enough for industry because until you get to the point where you actually have a good revenue and scalable and predictable and repeatable.
Back to Rick's point on that last panel, you're not soaring until you've enabled the real business model.
Right.
It's not about the aircraft, it's about how that aircraft delivers on the business value.
Exactly. And that's, we look at the ground-based. So we didn't go with ground-based because that's not scalable. If I have to put out $1 million of radar every 10 miles, I can't afford that, so our company doesn't work.
You're getting radars cheap. They used to cost me $10 million.
Obviously, I don't buy them, so it's just pulling a number out. But it's that sort of challenge. So how do we find something that does work that way, and how do we find something that doesn't stress the system from there? And I think that's part of that balance challenge of understanding the safety case, but it can't be so safe that it doesn't make money.
That's a tough challenge. It really is. And as Dallas said, it's not our intent in the FAA in ensuring that the system stays safe. Right. We never intend to destroy business models or crush business dreams. But sometimes it's kind of hard for both of us to know where that line is. It really is. So another, maybe not as big as GE, but not a tiny company, Precision Hawk. Ali, you must be seeing the same challenges, and I know you've been looking into some rather interesting technology.
Absolutely. So just to give folks a little bit of context, in case you're unaware of Precision Hawk or the kinds of things that we've been doing, although I appreciate the shout out, Jonathan. And I too actually love to follow Dallas because he continually refers to me as young.
I know.
Which I enjoy immensely, so take notes, Paul.
I think he meant the industry. Oh, sorry.
Ali
I said I don't
industry.
mean to crush dreams.
Precision Hawk was one of the original Pathfinders, and our focus was on beyond visual line of sight operations, but specifically those beyond visual line of sight operations that got us sort of initially, we called them sort of localized beyond visual line of sight. So we weren't looking to swing for the fences initially and fly coast to coast. What we really wanted to do, and what our commercial clients really wanted to see from us, was that we could fly just a little bit, initially just a little bit farther than the visual line of sight standard, and that's what eventually became what is now the Visual Surveillance of Airspace Limit of BVLOS, the operation formerly known as EVLOS, for the old folks in the room. And then sort of grew, the last part of that research grew from there. So the idea was that we wanted to see initially what could be done by a solo remote pilot in command, where they're, rather than looking at their drone, their head was on a swivel, and they were scanning the airspace for any incoming manned air traffic. So that was the first year and a half of the Pathfinder research, and that yielded our first commercial waiver for BVLOS operations, provided that the drone remained within a couple of miles of the RPIC. We are allowed to situate a remote visual observer that allows us to extend that range, but again, neither the pilot nor that remote visual observer is watching the drone, right? The drone information is being displayed on the GCS. So our waiver in that case was 107.31 and 33B. So we did not seek a waiver to 107.37. We are more than happy to get the heck out of the way if it comes down to that. So, so the latter part of the research, which is I think probably what's of most interest to this panel, was then, okay, so given that we were able to demonstrate that that operation can be done safely, and we have been executing it incident-free for the last 2.5 years, what is the next step, right? What's the next increment that we can grow beyond? And if you want to move beyond the point at which a human, right, the Mark I eyeball, can clear the airspace, you know, attached to the human brain, then we need to start employing some kind of technology or system. And so that was the second part of the Pathfinder research. One, how do we combine cooperative information? So if we know if the manned aircraft is not sort of cooperative drones, but cooperative manned aircraft, if that manned aircraft is transmitting its information, how do we use that in combination with a DAA system that helps us to plug that gap of non-cooperativity? So for those of you who operate primarily, as we do, in rural and remote environments in Class G, you'll know that there is a few folks out there, and they're not always squawking, right? Agricultural aviators are one of our favorite groups. They're often in the same areas that we are. So we really needed something, and much like Jonathan, for those kinds of ConOps, a ground-based solution wasn't ideal, simply because we didn't have any sort of planned infrastructure that we had the expense to situate some kind of ground-based detection. We really wanted something on the drone so that that DAA protection was carried around with the drone. So during the Pathfinder experiments, I opened up the test bed, and with some cooperation from Ted's former colleagues at MITRE, they invited some of the DAA providers to come on out and use the fact that I was flying a manned aircraft. I don't know if K-State's in the room, but they were the ones who were flying the airplane for me. We used that to have some folks come out to the field and demonstrate that their DAA system could provide the kind of coverage that we were looking for. And the one that we eventually went with is a solution by a company called Sarah. It's called PANCAS, and I am sadly known for perpetually getting this acronym wrong. Passive Acoustic Noise Canceling Airborne System, something like that. Anyway, if I check my email later, I'll have an email from the CEO telling me I got it wrong. But anyway, the point being that what we liked about it was that it was a passive system, so the swap requirements were not very high. It provided 360 degrees view, 180 this way, 360 degrees view of any aircraft, and it also was very lightweight, right? So we were able to mount it on board without any difficulty. It had a very, very long range attached to it, so some of the outer limits of the points that we've seen were on sort of the 4 to 5 kilometer range, which was very close to the kind of range that was available with the human eyeball, actually, right? That was so it was sort of, the way I think about it, I'm often asked to describe things in not very technical terms, so if you want the technical stuff, come on up and ask me later, is that it's like I've taken my EVLOS observer, right? It's like I've taken my person and I've sat them on top of the aircraft, and now rather than having this sort of locus of protection around the pilot themselves, that locus of protection with the DAA system extends around the drone itself. So that solution is in the works. I will say that for those of you in the room who are innovators and are looking to build BVLOS systems, one of the consequences of the fact that we've had some trouble, I think, as an industry getting to this operation, is that when we went looking, we're not a hardware provider at the present, or not a hardware designer at the present time, so we went looking for a solution. And the bigger challenges were actually not the DAA system, it was that we needed something that could fly the ranges we wanted it to fly and carry a heavy payload. A lot of our customers like a LiDAR platform, so getting something that can stay under 55 pounds while it's carrying a big payload and maybe half a tank of gas, and has the comms to get out to the distances that we want to get at. That actually was more of a delay for us than the DAA system, which was the PANCAS system had undergone, beyond what we did under Pathfinder, had undergone a wealth of testing, including with the Air Force, which I wish I was doing research for the Air Force because they have so many cool planes. Man, you guys should see this report. It's the best. They've got like 8 different airplanes. They probably just had them hanging around in the backyard, right? And I'm struggling to get
Go to Arizona. They have a whole bunch of them parked there.
Yeah, I'm really jealous, right? Like speaking as a researcher, terrible. Anyway, so I think for once I was not as long-winded as Dallas. Usually.
But I'm going to help you by augmenting. Okay. And Ted, we haven't forgotten about you. And just to foreshadow you, Ted's got a whole different approach to DAA. We're going to get to in a second. So keep your attention high. But you mentioned the Mark I eyeball, and I know, Paul, we hear references to it in safety cases many times. I've got several friends, one of which I have a contract with for about 29 years, human factors expert, and they're sort of quizzical on why we in the drone industry are so focused on what we call the Mark I eyeball when we're really referring to the whole system. And most of the time people are referring to visual acuity, or how good is the eye at detecting an object. And it's some of their viewpoint, and we'll come back to this. This is a teaser question. We'll come back to it, but they think we might be giving too much credit to the human system for attention and focus
100%.
and the central processing unit that after it goes from the eyeball to the occipital lobe and it starts running around and goes over the corpus callosum to the other side isn't necessarily as good as a machine that never fails in having attention.
I'll tell you what, both of the Pathfinder results are public, right? Both my phase 2 report, which was very focused on the human system and how and what factors might affect the human system. And I came to MITRE at the beginning of that research, and we sat down and we came up with a list of some 100 variables. And those of you that are in statistical research are doing the experiment design in your head, yes, it is just that terrible, right? So we came up with a list of all the potential variables that could affect the human system. So that report, long, complicated, a lot of graphs, right? The report where we replaced, or whether, I'm not going to say we replaced the human system, it's that we let technology and machines do what technology and machines are good at, and we let humans do what humans are good at. Right, which is not necessarily
That's what good human factors
visual
engineers
detection.
will tell you is an optimal design.
That's right. So that's the split we made, and the experiments and the results were just that much simpler. Because although there is a number of variables that will ultimately affect these technologies, the human system, the reason, if I can offer my opinion.
Absolutely.
Right,
That's why we have you here, Alan.
The human system, right now we're iterating, we're expanding around that human system, not because it's the optimal system, but because it's the one, frankly, the FAA understands the best right now.
Well, we as humans have a lot of confidence in it.
Yes, right?
We do.
Well, we do.
But what we're doing today has nothing to do with replacing the Mark I human eyeball. If it were, we would only have to worry about 135 degrees field of view out of a typical aircraft, about 30 degrees elevation view. Our detection range would be well inside a half a mile, and with stuff coming right at us, we'd never see it. So,
see, I wish it was that easy for the
I wish.
application.
So I remember being on the complaining side about this 12 years ago, because at the time there was no Part 107, there was no Section 3, there was none of that. They were just holding us to 91-113, the well clear standard. They're saying you've got to be able to replicate that pilot function. And we're like, well, that's easy.
Yeah.
We can do that now. We're like, no, you really can't. But in reality, though, what we're trying to do today is not about replacing the very fragile capabilities of a human being. It's about exploiting technology to get the best answer that we can get.
So speaking of technology, nice segue. Ted, we've heard from the regulator, the researcher, the operators, and it's all been very much focused on an aircraft-human sort of balance. But AROS has a slightly expansive view. My understanding, how does DAA fit in your larger UAS traffic management framework?
That's a great question. So so I'm with AROS, and it's a UAS UTM ecosystem provider, trying to tackle the really hard problems beyond visual line of sight, one-to-many operations. And as part of the UTM ecosystem, I kind of look back into what Paul actually had a slide up on his brief this morning about the ICAO conflict management model. And I think it's a really good way to break down the problem of detect and avoid, see and avoid, sense and avoid into kind of 3 layers. And so the first layer is strategic conflict management, which is what happens before you take off. So in the manned world, that's airspace structure, that's the hemisphere rules that says what direction you fly, at what altitudes. It's managing arrivals and departures so that you don't have too many people at once. Airport traffic patterns, that's all done before you take off. That's the strategic layer. Then you have, the next layer you have is the separation provision layer, often called the tactical layer, the remain well clear layer. And this is what air traffic controllers do. They provide 3-5 mile separation using technology, not using their human eyeball. But they also do visual separations. They often tell pilots, maintain visual separation. Once you see them, you follow them in, you remain well clear, and that's perfectly safe. And then even general aviation pilots flying VFR do sense and avoid, see and avoid at fairly reasonable ranges because they know where to expect traffic and where to look. So that's the separation provision layer. And then the final layer is the conflict avoidance or collision avoidance layer. And that's, for manned pilots, that's the, oh shoot, there's an aircraft, pull up and maneuver pretty hard. Or if you have TCAS on airliners, that's the climb that you get through the TCAS layer of protection. So those are kind of the 3 layers of conflict management. And so as we start to look to the future with UAS, they can kind of have all 3 layers, same thing. So first off, you have the UTM providing services to help do some of the strategic layer. So before you take off, you can look at airspace risk and figure out where areas of more and less risk. Like I know there was a gentleman earlier who asked a question about ultralight operations and parachute operations. Well, we know a lot of where those happen. There's a site near where I fly that has parachute operations. And so you can start to deconflict from some of those strategically. Let's just avoid the areas where we know that have ultralight or parachute operations. We can also deconflict from other UAS trajectories. So a lot of the initial NASA UTM studies, the TTL studies, have involved multiple aircraft being operated by multiple UAS service suppliers, USSs, developing deconflicted trajectories. And so assuming everyone stays within their corridors, they'll be deconflicted before they even take off. So that's the strategic layer before you take off. Then the UTM ecosystem can also help with that middle layer, the tactical layer, the separation provision layer. So these are more decision made once the aircraft has taken off. So the UTM system might be a surveillance service provider, and so it could pull in FAA radar data, maybe some private radar data, other surveillance ADS-B information, and could provide that information to the pilot in the ground control station. They could do conflict alerting, so that when a non-cooperative aircraft comes in the region, you can start to make decisions about your maneuvers or deciding to land or reroute yourself. The other big part of UTM is giving priority to our public safety operators. So you may have a corridor that's all clear and good to go when you take off, but then an EMS operation needs to come through there, and you need to be able to dynamically reroute yourself around there and remain well clear of that EMS helicopter or drone in the future. And so that's kind of the tactical layer where you're trying to remain well clear, as Dallas talked about, the well clear standard. That kind of sets the level of performance, and then the UTM ecosystem and the various services under that ecosystem can be used to provide some tactical avoidance once the UAS is taken off. And then the final layer is the collision avoidance layer. You know, the FAA has invested through the TCAS program office and the ACAS SXU, XU for small UAS. Likely that layer of protection will probably be more onboard, you know, whether it's with an onboard radar or onboard vision system or a, you know, something like that, just because the time scales and the distances are so short that it's tough to rely on both the C2 link to get down to the ground control station, have the pilot have time to react, upload a new maneuver. So that likely will be, you know, in the future, more automated and more on board the aircraft. So that's kind of the three layers. I think, you know, you asked, Jay, an earlier question about some of the biggest challenges. There's still a technology challenge, you know, and it is, you know, to be honest, it's radars and EO sensors. You know, I think there's a lot of work, standards being developed for them. But the technology still needs more work to detect, you know, non-cooperative manned aircraft at appropriate distances to remain well clear.
So that, oh, sorry.
Yeah,
Please
no, I was
finish.
just saying that I think that is still the biggest hurdle to at least the detect and avoid side of beyond visual line of sight operations.
Well, you teed up the first question we got from the audience very well. So I'm rephrasing it, but the question was basically, if we had no non-cooperative aircraft, manned aircraft in the system, how would that change detect and avoid? And I'd like to add a follow, I know it's almost a tautology, isn't it?
I think we owe that
But
one
I'd
to
like
Ally.
to add a follow-on, and it kind of goes to a point you were making or alluding to. Is that even an achievable goal? Or given our aviation system is trying to achieve that one with nothingness nirvana, really, can we ever have cooperative, all aircraft operating in the airspace cooperative? And I'll leave that to everybody.
I was going to say, who gets to answer that first? We can't even mandate every aircraft has a radio, right? I mean, that's one of the big challenges. We talk about cooperative and beacons and all these things. There was a previous panel where they talked about the ability for like ultralights to have a remote ID detection system and things along those lines. And I love it. I mean, 15 years ago, Dave Voss came in, we still work for Athena, and said, I have a plan for ADS-B bubbles around everything, and it'll be detect and avoid. And it'll be great because everything will run ADS-B. And we all sat there and went, yes, if everything's running ADS-B and everything's cooperative, we have a fantastic 99% answer for detect and avoid because we all know exactly where we are.
Which is like the mice belling the cat.
Right.
So, yeah.
And then at that time, we also said, but we can't even mandate aircraft or have radios across the board. And so here we are 15 years later, and that still hasn't changed. We finally got to the point where we're mandating ADS-B for the most part, but we still have, you know, those systems that aren't going to be ADS-B equipped and aren't going to be cooperative, and they're flying in our playground where the UAS want to fly and need to fly. You know, the number one answer that I always come back to, and I apologize, I feel like I got shafted on not getting 15 minutes. But the thing I always come back to is when I used to fly helicopters for a living and in southern Louisiana, coming in on a beautiful instrument approach and watching the crop dusters flying around on my back ILS, and there was no one on the radio and no way to do anything to Alexandria, Louisiana. And so with the statement we had earlier about how much credibility we give the human system, I think we give it far too much. We're treating them like Chuck Yeager and, you know, Neil Armstrong and not the 13-year-old who's out soloing, right, which is, you know, kind of our bracket there, and really put this higher level of performance that may not be there. So,
Allie, you look like you want to add something.
I more or less always want to add something.
Okay.
Yeah. No, I think...
Again, that's why we have you here.
I mean, the perspective that Ted just espoused is obviously, in my mind, as when we have a UTM system or a distributed architecture that represents UTM, the more we can do from a strategic deconfliction perspective, right? And like this kind of early tactical layer of deconfliction, the more we can do there, the safer everyone becomes. But it's never, you know, even you said, even if they mandated these ADS-B bubbles, that's still a 99% solution, right? And it seems that the regulatory challenges associated with making a space completely cooperative are just insurmountable. So to answer the audience question, yeah, if we had a fully cooperative space, oh my God, I could maybe finally sleep at night again, you know? But the point is we're never gonna have that. So I think what we need to find, there needs to be a recognition that what we're seeing is that there's going to be sort of a sliding scale of capability in environments, right? And that DAA
We hear that a lot in this space.
Do you hear that?
Yeah, no,
I know,
but I
like
think
It's a
I said
spectrum.
that
it's a spectrum.
Right.
yeah, the risk continuum. It's a
Precisely.
fundamental principle to everything we're doing in this space.
And it's encoded, I mean, I think in the previous panel you mentioned the Jarosora. It's encoded, for example, in
Right.
the Jarosora perspective, which I think is really good, where they've taken this kind of continuous space. This may tee up your standards questions. They've taken up this continuous, you know, spectrum of ConOps that are BVLOS and kind of successfully chunked them into buckets.
Right.
And it makes it more possible for those of us that are operators to try and figure out, okay, which bucket do I fit in?
But for that to work, we have to have the regulators agree to the bucket.
Absolutely.
Right.
So when I'm solving a problem for rural Nevada, and I get the question of, well, how would that work in downtown Manhattan? You know, it's hard to not answer. I don't care. I'm not flying in downtown Manhattan. I'm flying in southern Nevada with 2 people per square mile for population. And it's sometimes we have that challenge there, and not as a jab, but that becomes a challenge of we have a continuum. We accept there's a continuum, but let's not just pick blue as the answer in that continuum.
Right.
Yeah, and I do think, you know, along those lines, the SORA did a very nice job of breaking down the air risk class into 4 levels: high, medium, low, and basically NA. And I think both, you know, so I serve on both RTCA SC228 as the detect and avoid lead, and also in the ASTM F38 effort. And they've done a nice job splitting it up, and that RTCA handled the high-risk airspace, the integrated airspace where you're with commercial aircraft, you're flying IFR, you're receiving air traffic control services. That's been kind of the domain of RTCA. And then ASTM's handled the low and medium risk airspace for the SORA, where you're not operating under IFR, you're not receiving air traffic control services, you're below the altitude where, you know, TCAS can be set off. And so I think there's been a nice division right now, at least to enable initial operations. I think where both RTCA goes in the future, where ASTM goes in kind of the next revision, I think we'll see. But to now, I think we have binned it pretty nicely, and those 2 standards committees are each addressing their own portion. And I think, you know, hopefully we can get standards published and the FAA can accept them. I think that's been one thing that's held up a lot of this, you know, standards work, is then waiting on the FAA to then accept the standards. And the FAA did accept the RTCA standards through the TSOs. But how the FAA accepts ASTM standards through notices of acceptance or whatever is still
We're working
in the
on
works.
that.
Yeah, right.
We are. We are.
And don't let this stop you. So that, I hate it when people use circumstances as an excuse to not work. So I can't recall the time in the last 15 years that I've been working exclusively on unmanned systems where someone brought the FAA this brilliant technical solution. They said, yep, you're good. It just hasn't happened, right? And so if you're working on that model, you probably need to find another line of work. What has happened time and time again is that it starts out with proving I can do a little bit, and then I can do a little bit more, and I can do a little bit more. And the FAA as a regulator gets comfortable with, okay, you've been doing this a couple of years, and so each time we give you a little bit more room, and you still continue to demonstrate you can do it well. And after a while, that gets codified into here's best practices. Those best practices eventually make it into rulemaking, and then that rule eventually gets let. That's how it's worked, right? I can trace you the origin of Part 107 back to the original 2007 DoD-FAA Memorandum of Agreement. And it over that 10 years, it was just a matter of walking those steps. So for you, you may want to fly in downtown Manhattan, and that's a wonderful, wonderful thing. But don't let it stop you from flying in Kansas now and showing you can do what you think you can do, and then working your way to denser and denser areas with better and better technology.
And so it's not to sound down on it. I mean, it works. In the year and a half since we first got our 107 BVLOS waiver, you know, last month we had 2 over 55-pound BVLOS day-night up to 2,000-foot approvals using the growth of those same processes. Yep. So it does work and it does happen. We're no longer in the show me a rock, right? We're past the does it look like a duck, quack like a duck, and now we're putting bills on beavers. All right, so we've got these things that
Putting bills on beavers?
to make it look like a duck.
Oh, I
Right?
think that's a platypus.
Keep up.
So can I add a little bit of color to that statement?
The bills on beavers?
No, that's plenty colorful. No, to Dallas's statement. I'm a big believer in incremental growth with the airspace, and in sort of as an industry that we move forward and we understand the next step before we take it. And I very much feel for flight standards and their job because you're being often asked to evaluate risk in scenarios that are perhaps not as well known.
Right.
The one thing I would say is this, as someone who was involved in a FAA research program, Pathfinder, who's been continually involved over the years with Assure, the one thing I would like to see is that as research results are completed, promulgated, sent out to the industry, that there is an understood method for taking those research outcomes and giving them to the regulators in such a way that they feel more empowered to make regulatory decisions moving forward.
What would that look like, Allie?
Oh,
I actually have a proposal.
Oh, no.
Oh, you're going to add color to Allie's
Go ahead.
color?
let me finish my sentence
I
and then
absolutely
you can
will.
tell me how it's really done. Because just to use the Pathfinder as an example, right? One of the things we had to do as part of our Pathfinder, because we were still very much human in the loop, was we had to bring a lot of pilots onto the field to come up with reasonable statistical distributions of how far away they could see things, what reaction times looked like, et cetera, et cetera. That is not, the whole reason that that result was done and then made public was because it was understood, right, and part of our mandate from the FAA when we started the Pathfinder, it was understood that, your average operator is not going to be able to mount that level of experiment. And that's precisely the kind of thing, I mean, Jonathan works exceptionally hard all the time, but
All the time.
But I mean, this is the kind of thing too, where when the original categories for Assure and the follow-on know what the heck to do with all this.
Right. So from my point of view, I think, and I made the plug for this in the BV Lost session, is I see in the, like ASTM F38 as a forum for capturing the work that like the Pathfinders or other companies that are on the leading edge, they're giving us reams and reams of data to get a waiver, right? And we spend a lot of overhead to understand that. If we can capture that in a standard, whether or not we put out something of a notice on the Federal Register, I think we, as regulators who also participate in those consensus standards
I
organizations,
feel like I've seen you at the
will
meetings, Paul.
understand, what people are talking about if they reference a standard. So I think it's not necessary for the standard to officially get adopted in the Federal Register or, through rulemaking for it to be useful to the FAA. I think there's a more direct path that can certainly be achieved where, maybe it's not the complete solution, which is why it might not be, in regulation, but it'll at least get us to the 90% solution. We can have a shorter conversation with an applicant and, fill in the gaps where they exist.
But that gap, and this is specifically where Allie was going, she and I are of a like mind on this. We are in so many things, mainly because I say yes a lot. There is still a difference between the output of research. So, for example, the Assure universities, when we do projects for the FAA, our product is a report that says, here's the data that we analyzed, here's the impact studies that we did, here's the existing body of literature that's already out there, and we come to these conclusions, right? These conclusions are codified, they're formalized, they're accepted, and then what? There's a spread there between the end of that research and the process that it takes to turn that into specific regulatory recommendations that can be enacted, right? And there's that gap is not necessarily completely fillable by the FAA because the technical side of it, right? They're not experts in everything, and I say that at Assure we are, but but within the broader community we certainly are. So that particular piece, as opposed to handing you, here's great research, go do something with it, right? Instead of, here's great research, here's how that research translates into specific modifications to policy, procedure, advisory circulars, orders, doesn't matter what it is. And then those standards agencies can take that and immediately work with it, right? Because what standard agencies don't do, ordinarily in the course of their actions, they review the body of work that's out there and they do consensus-based decisions, right? Contrast that with how the SARP works. Ted and I over the past few years, is the SARP takes data and research and models the crap out of it, right? We've run millions of models. We do experiments after experiments. We hard validate everything and come up with a hard scientific answer. It's not just yes or no. It's 1.65 is the answer, right? So, but the SARP can't do all of this. The SARP does one project a year, essentially. And so there's this crying need for another place to fill that gap of putting scientific rigor to the end of research and turning it into recommendations. And we're actually in conversations within Assure about standing up a capability that would do just that and do it for everyone. And so that aggregator, that consolidator, and that validator of that kind of data, that's a role that we think it sort of needs to be filled, and we've got a proposal to help do that.
Yeah,
Well,
there's an equivalent issue, right? So that for those of us that have perhaps been involved in commercializing technologies that have been generated by research, it's the proverbial valley of death, right? You get to the end of the research, you do not yet have a viable product. And this to me is like the valley of death, the government regulations edition, right? We need something. So very often the way companies overcome that valley of death is either by putting in a lot of their own money or accepting support from other programs. There needs to be something that sits in that role.
So you've done a nice job of framing what I would like to use our last
You're
few
welcome.
minutes. Thank you. I apologize for not saying thank you. Ted, we're going to start with you. What do we need to do to get out of that valley of death on DAA? We've heard a lot of good input. We've made a lot of progress on DAA on some fronts, but we're still not there. I hear policy. It sounded like a pretty firm consensus that with things like SORA and others, we have the policy basis for understanding. If the solution was brought to us, we could figure out how to approve it. But what do we need to get us out of the DAA valley of death?
Yeah, I think I would say two things. I think first off is finish up the standards work. I think it's much easier to tweak a radar or train a camera to do something if you know the bar you're trying to achieve. And so as Dallas mentioned earlier, it's about setting the well clear standard and the performance associated with it. I think once that gets published in ASTM, RTCA, and FAA gives a head nod that would be acceptable if somebody met it, then I think the technology folks in industry can go off and make that happen. But I think right now they're reluctant to invest the money to change the design of their radar or redesign their cameras until they know what they're trying to achieve is going to be acceptable.
So the investors have to see a path to success.
They have to see a path to acceptance.
Path of
right?
certainty, yes.
Yeah.
We're getting to you, Dallas. Don't jump the gun. We got to give Paul a chance.
Yeah, Paul.
Paul, from the regulator, how do we get out of the valley of death?
I think, so my take is that we need to drive more participation to accelerate the standards development. I think the standards development cycle
So again,
without the right
complete the
participation
standards.
is a little bit stagnant, and driving more people to share their data. A lot of people come to us and provide a lot of data to support their waivers, right? But if we can get them to kind of share with the broader community, then I think that'll help accelerate things a little bit. To better understand what you need to pick up on your sensors for specific, types of airspace and stuff like that. So I think there's there can be a lot of benefit from more collaboration. But I think, yeah, he's right. Standards is the pathway to at least be speaking the common language. So then when people have a solution that meets a standard or is close to meeting a standard, we have less to talk about. We just have to talk about the gaps.
The final gaps. Okay, Allie?
If I can get a little specific about this for a minute. So I am 100% in agreement with the statement that the standards are going to play an important role here. I chair the test methods working group for DAA, for ASTM, so I'm obviously on board with the standards perspective. I also know that as a commercial operator today, I cannot wait until those standards have been released and approved to continue applying for waivers. So if I think my colleagues here are going to perhaps be commenting on something a little more expansive. If I could suggest something that I think is a very near-term need as we're getting additional participation and sorting out these standards, I think that if there is we can get to some consensus or some agreement on what an appropriate set of test artifacts for a safety case would look like. Because I think this is where I think flight standard has a challenge, we have a challenge. We don't want to come to you with like a bloated, reams and reams of stuff. We want, and even to help the standards development, even on my own test methods group, to understand what kinds of, and I said this could be real specific, but what kinds of artifacts are really kind of necessary as you're looking at different DAA strategies. It's not going to be the be all end all, it's not going to be the magic pill, right? We may have just exited baby flop, beer belly,
Sweat.
beaver bills, whatever it was, right? We may still be there, but that there's some, understanding and some feeling of confidence on the regulator side that like, okay, yes, I see you've brought us something that we are maybe expecting to see. And I think as a near-term discussion, even to support the standards work, that's a useful thing to do.
Excellent. That's a really good point. Jonathan.
So I think we've run into an area where sometimes we'll shop for inspectors, right? This happens on the traditional operators where the right person to talk to get certain things.
Do you really want to admit that in front of this crowd?
Well, no, I'm saying on traditional side. And what it looks like is making sure the right rules. And there was a comment earlier about not trying to force 107 to match 135 and vice versa. And so I think part of that is you've got to know what you're looking for and what the regulatory framework to go after. But the second piece of that is that, we have lots and lots of standards that are out there. And there's been plenty of applications. Our first BVLOS waiver went in using an ASTM standard for BVLOS. We've gone in with a number of these standards. And sometimes the feedback coming back isn't about the standard itself, it's about the one-off unique situation. And then you go to a different certification method or operating approval method, and it's completely understandable and accepted. So I think some of that internal challenge in education of here's the standard, how it exists, and a proper application compliance with that standard looks like this. I think that would be a very helpful
Against this
piece.
regulation.
Against that regulation. Kind of like what we do with LSA, light sport aircraft.
Yeah.
We have a great matrix that says if you want to build this type light sport aircraft, you follow these ASTM regulations and match compliance and you're in.
Okay, Dallas, you get the last word.
After everyone else has already made all the points I needed to, so thanks, guys. And Jonathan's point about matrices, before you get off of that, Jonathan's done more than anyone I know in ASTM to actually turn the standards work into those kinds of matrices that are easy to follow and assign and prescribe. So congratulations on the work you've done there. For me, I see, we talked earlier about a risk continuum, right? About it's not just a line of success or not success, but a continuum. I also think that a process continuum is important. So, for example, while we use performance-based standards as a method of saying, we're going to give you guys the opportunity to come at this problem in a lot of different ways, there's a very large group of you that kind of want to do the same thing, right? With a small category UAS, you only want to go so far, et cetera. And just like with 107 and everything else that came before it, you would be very happy with a prescriptive answer. You'd be, okay, within this box, this tells me if I do these following things and I check these boxes, then I can fly, right? Because you don't necessarily need to develop a very unique solution for your very unique application. You just need certainty within the box that you want to operate. So I think that process continuum is important there as well. Just like we do for BVLOS waivers and night flight waivers and everything else, pretty soon people figure out that I copy the way Jimmy did it and I'm going to get a yes. So a prescriptive answer for those low risk situations, right? Smaller aircraft flying low population density areas is a good thing. We don't need a performance standard for that. As the risk increases, then the policy gets tighter and you have to present more evidence. So I think a mix between prescriptive and performance-based would be tremendously helpful to the lower end of this industry in terms of investment levels in staffing and technology.
All right, with that, thank you, Ted, Paul, Allie, Jonathan, Dallas, for your thoughtful words this morning. And I thought some very nice, good banter. Not all the views were cooked up and together. That would be quite dull. Apologize to Ted and Dallas for screwing up your introductions. To you, the audience, again, thank you very much for your time and attention. Thank you for your questions, and have a good symposium. Thank you very much. Eric, are we on break? And Mr. Amend asked me to remind you that we are on break for 20 minutes.
Just put your arms around